Hi. In this question, we are going to look at a quadratic equation and we are going to prove some properties about this. So, given that A, B, C are odd integers, we have to prove that ax squared plus bx plus c equal to 0 cannot have a rational root. So, what I will do is I will show you two proofs for it. So, try this out yourself, and if you don't get it, you can refer to this video. So, the first proof. So, we'll first argue by contradiction. We'll say that suppose P by Q is a rational root for this quadratic, right? Where P and Q are not both even. Obviously, they should not both be even because then you could have cancelled a factor of 2 from both of them, right? So we'll say that, let's say P and Q are not both even. So first thing that we'll show is we'll show that neither P nor Q can be even. How do we say that? So we say suppose P is even. Suppose P is even, right? So if P is even, we can say that the equation A P by Q square plus B P by Q plus C must be 0 because P by Q was a rational root. So we simplify that a little bit. It becomes AP square plus BPQ plus CQ square equal to 0. Now, if we suppose that P is even, then AP square becomes even and BPQ becomes even. But we know that Q was odd and C was odd. C was odd was given in the question, and Q we are assuming is odd, right? Because we are saying that we are supposing P could be even, then Q is odd, right? So this term is odd. So obviously even plus odd cannot be 0 because even plus even will be even and even plus odd will not be equal to 0 then, right? So this is a contradiction. This is not possible, this last statement, right? So therefore P is odd, right? We can do the exact same logic and show that Q is also odd. Q is also odd. How? We will say that basically suppose P is odd and Q is even, right? So that will make this one even and this one even and this one odd. And again, the exact same logic. So we get Q is also odd. Great. So we have shown that if P by Q is a rational root, then both P and Q must be odd, right? Must be odd. Okay, great. And then what happens to this expression then? AP square plus BPQ plus CQ square equal to 0. Now, we already know in the question that A, B, C are odd. So, and if P and Q are also odd, then this term is odd, this term is odd, and also this term is odd. So again, we come to a contradiction, right? Because the sum of three odd numbers cannot be 0. Why? Because two odd numbers will make it even, and even plus odd cannot be 0. Right? Can't be 0. So basically, we have arrived at a contradiction here, and therefore our initial assumption must be wrong. So P by Q cannot be a rational root. P by Q cannot be a root, basically, right? So that is the first proof. We can do it in a different way as well, which is also a proof by contradiction, but that is a different way of doing the same thing. So the second proof follows like this. We know from the theory of quadratic equations that ax square plus bx plus c is equal to 0 has rational roots. If the discriminant, which is b square minus 4ac, is a perfect square, right? Perfect square. So we will use this condition. So if this equation has rational roots, the discriminant b square minus 4ac must be a perfect square. So it should be the square of some integer. Now think about it. B, A, C were all odd, right? That was given in the question. So b square is odd and 4 times AC is even actually. So odd minus even will give us an odd number, right? So this whole number is odd. So therefore, when we write it as a perfect square, it must be the square of an odd number. So we can say it is the square of some number, 2n plus 1 whole square. Why are we saying 2n plus 1 whole square? Because b square minus 4ac itself was odd. So it must be the square of an odd number. So if we write it like this, we can expand it like this. And we can say b square is equal to 4 times n square plus n plus ac plus 1. So we rewrite it like this. B square minus 1 is equal to 4 times n plus 1 plus ac, right? So this equation is what I want to analyze. Let's look at the RHS of this equation. Now you can realize that a times c is odd and this is an even number. N into n plus 1 is even because it is the product of two consecutive numbers. So one of them has to be even. So this is even, AC is odd. So when you do even plus odd, the number inside is odd, right? The term inside the bracket is odd. So therefore has no factor of 2. Has no factor of 2. What doesn't have a factor of 2? N plus 1 plus AC, right? So therefore, we know that the RHS is divisible by 4, but not divisible by 8, right? We know that the RHS is divisible by 4, but the term in the parenthesis has no factor of 2, so it is not divisible by 8, right? Let's look at the LHS now. B square minus 1 can be written as B minus 1 and B plus 1. But we know that B was an odd number. So B can be written as B is 2k plus 1. Therefore, B minus 1 becomes 2k and B plus 1 becomes 2k plus 2. We can take 2 common here from both the terms and you get 4 times k into k plus 1. And now you will realize that this number is actually divisible by 8. Why? Because 4 is already present and k times k plus 1 is even because it's again a sequence of two consecutive numbers multiplied together. So one of them has to be even. So we are getting LHS is divisible by 8, whereas RHS is not divisible by 8, right? So that becomes a contradiction for us, right? There is a contradiction. B square minus 1 can never be equal to this. Therefore, our initial assumption was wrong. Our initial assumption was that it has rational roots from where we got this condition. So we have proved basically that if A, B, C are odd numbers, the quadratic equation cannot have rational roots. And we have proved it in two different ways, employing proof by contradiction both times, right? So hopefully you will also learn how to apply proof by contradiction in many different problems. And stay tuned for more questions. I'll be back with more content for you guys. Please like the video and subscribe to the channel if you have not done so already. And I'll see you next time.